This is the last topic of processor performance analysis. So you have to understand that in an pipeline processor, that is, if there is no hazards, the CPI value would be 1. But if load or branch come, like if we see load, use start. In the case of load instruction, we use plus 1 cycle per occurrence, and with the branch predictions, we use plus 2 cycles per occurrence. So in real world scenario, what happens is that load and branch can also occur. So the CPI value can be greater than 1 in when stall and flushes and all come. What happen is that the CPI value can be greater than 1. So pipeline issues one instruction per cycle ideally, but stalls and flushes can hurt this. So you have to understand that in an ideal pipeline, what happened is that the time period is depending on which stage takes the maximum delay. That is, which stage would take the slowest time to complete. That is dependent. So if you have a lot of stages, the stage which take the maximum delay would be the stage which would give us the, and that stage will decide the pipeline's the clock period. So for different stages, for fetch stage, for decoding stage, for executing stage, memory stage, writeback stage, for all these stages we have a clock period that we have to learn. For fetch stage, the PCQ, that is from PC register to clock 2 queue. From the PC you are taking to the PC we are taking the instruction. So that time period, and memory, instruction memory reading period, and setting up the pipeline register. So these three factors adding up would create the clock period in the fetch stage. So PCQ setup as well as read. T memory means T memory means what? Instruction memory read time. So all these factors add up together would decide the clock period in the case of fetch, which and all the T PCQ is the memory is the, and the setup is the. Setup means setting up the next pipeline register is what. In the fetch stage we will set up the decoding stage pipeline register, right? See, so in this is the fetch stage, and we will set up what? This is the decoding registers, decoding pipeline register. So we have to set up that also. That time should also be included here. Understood? Now decoding stage. If you consider the decoding stage, we have to read the value in the register file, and also we have to set up the next registers pipeline register, next stages pipeline register. Now you are doing this 2 times because decoding stage can be come here, after the write back it is going again to the decoding stage itself, right? So what happened is that the register file is read twice. So that is why we are taking here the factor 2. Understood? So this is the clock period of decoding. Now for executing stage, if you consider, this is the longest path and this is the longest path. Okay, so since this is the longest path, this would determine the clock period of the pipeline register, because this is the longest path, right? So in the executing, the time period of ALU and OR operation, then time period of setting up the next register. Now there are muxes. If you see how many mux are there in the ALU, see 1, 2, 3, and also there is an adder part also which is there here. If you see, mux value should be multiplied 4 times in here in the executing stage. And PCQ which is PC instruction, that is because if you see here we are adding PC value, current instruction value here to get the next target, right? So PCQ is also needed here. So PCQ for mux, and also the setting up ALU and OR. So these are the things that we have to add here. And or logic should also be there, and or logic. So these would be the longest path. Since this is the longest path, now why we are having different mux is there? Because first forward mux is the forward mux, the first mux we have. Actually you can see that For source B there is a mux, then forward A mux is there, forward B mux is there, then PCSRC mux is also there. If you see here, there is source A mux is also there, source B mux is also there, now forward mux is also there for B, and also there is a PCSRC mux. PCSRC mux would also be there for deciding this. This PCSRC mux would actually depends on the value which is coming from this ALU. That is for 4 mux we are basically multiplying here. Understood? Now, and you have to understand here we are using the PCQ value also, because we have to add, for branch case we have to find the next instruction by using current PC value, right? So that is why we are using the PCQ value. So this is AND OR logic is used for what? Branch decision. So we are using AND OR logic here. T setting up the next pipeline register. So these are the executing stage. So in the executing stage, this much we have to add, which is the longest path. Now memory stage is what? In the memory stage also, if you consider, memory stage is memory, T memory, PCQ and setup is only the write back stage. Also 2 times we have to access the write back stage. So PCQ, and there is a mux which decide, and also read the then you have the setting up the register file, because we are going back to the register file, so we have to set up the register file. So that is the things here, and we are doing it a factor of 2, because write back only uses the first half of the cycle, and then it is sharing the second half with the decoding. In the other case also, decoding also we use a factor of 2, because the first half is in that decoding, then the second half would come in the write back. That is why. So in the write back and decoding we use a factor of 2. So read file setup, and also there is a mux. That is why we are using, because we know write back there is a mux to decide whether you have to read from the memory or from the ALU source or from PC plus 4 value. So there is mux here. Now memory stage, we know memory stage is PCQ mem setup. So this is the complete, this all for fetch this equation. This is the complete formula that you have to understand for fetch, decode, execute, memory and read, write back. So first we have PCQ, memory and setup. That is the same thing for memory stage. Fetch and memory stage have kind of the same formula. You have to understand that. In decode and write back there is a factor of 2. Okay, but here RF read is here. First we will be reading from the register file, then T setup. Here is RF setup and T mux and TPCQ. Longest part is the executing part, which contains T setup, AND OR logic, ALU, for multiplexer and TPCQ also. So PCQ is there in everywhere except the decode. That you have to understand. In decode we don't need the PCQ value, but in others all, in decode we need only the RF read, that is register file read only is needed. Then T setup is only needed in the decode. But in others we are using TPCQ value also, and in the write back we have to go back to the register file. So that is why we are using register file setup in write back. So this is the final formula, and on this formula everything is questions and all is basically solved on the on which case, on the case of performance analysis of our pipeline register. Now critical path, if you consider, critical path here is the write WB pipeline register, then result W, forward BE mux, source BE mux, ALU, and so this is the critical path. That is, if you see, this is our critical path. Critical path, if you see result, then source B mux is the forward B mux is the, then this 0E value, right? Then we are going to where AND OR logic here. This is AND OR, ALU AND OR logic, then PC register. That is here. This is the PC register. So this is a control, the critical path. So you have to understand what would be the critical path in our diagram, which can be highlighted. So this is the then forward B mux, source B, then ALU, then this is our critical path. So this is one important thing that you have to understand, right? Critical path is this critical path which has the most delay, and this would be the path which has the most delay. So then you are going again to the PC register. So this is the important thing that you have to understand here about the critical path. Then we have understood comparing all these processes. Single cycle CPI is 1, performance is moderate. The multi-cycle CPI is 3 to 5, average, performance is poor. Pipeline is 1 plus small penalty will be there. The penalty depends on the stalls and flushes and all, but the performance of single cycle is moderate, multi-cycle is poor, and pipeline is the best. So single cycle has the longest cycle time, multi-cycle has the shortest, but medium pipeline has a medium cycle time. This is important. But performance best is pipeline, single cycle is moderate, multi-line is the poor. Cycle time, if you consider, longest cycle time is for the single cycle, moderate is for pipeline, and multi-cycle has the shortest pipeline. Why not exactly 5 into faster than the single cycle? Because there are some reason. Pipeline overhead is happening. We have to do pipeline registers, add this T setup and T PCQ value to every stage. So pipeline overhead is happening, and CPI value would be greater than 1 because of stalls and flushes. And unbalanced stage, execute is slower than others, so all stages must wait for it. So unbalanced stages is the now these are the reason why the pipeline is not 5 times. We have said that in single cycle 1 instruction is happening, but in pipeline 5 instruction would happen. So we are saying that pipeline can be 5 times faster, but that is not the case. The setting up the registers, pipeline overhead, that is T setup and T PCQ, would take some time, and CPI value would be always greater than 1 because of flushes and branches, flushes and stalls, right? And also there is unbalanced stages. So these are the 3 reasons why our single cycle is not 5 times faster. Our pipeline is not 5 times faster than the single cycle. And you have to also understand this critical path. Also you have to remember what is this critical path. This darkened lines are the critical path. That is, in the writebacks there is a mux, right? So this is the first, it starts from the writebacks pipeline register, and from there this is result W, and from there we will be going to the forward B mux, and then we will go to source B mux, then ALU, then AND or logic, then we are going to the PC register. This much we have to understand. PC register, this is the main things, that is, this is the critical path that you have to understand. And why, also you have to understand why this single pipeline is not 5 times faster than single cycle. There are 3 reasons. Pipeline overhead, CPI is greater than 1, and unbalanced stages. And also you have to understand this formula. This is the only things that you have to remember from this class.